Hi, I'm Chris Field. I'm the director of the Stanford Woods Institute for the Environment and a senior fellow at the Stanford Precourt Energy Institute. On behalf of both of those institutes, it's a pleasure for me to welcome you to this afternoon session on clean energy. At Stanford, we make a really big effort to be helpful in national and global dialogues about where the world's headed on key issues. And we try to do it in three ways. Sessions like this contribute in a fundamentally important way to two of those. The first is research breakthroughs that bring technologies and policies and institutional features into focus so that we can make progress on key issues. The second is engaging in a dialogue to communicate the implications of that research and the opportunities that it presents. And the third is to learn from stakeholders about what issues are important, what needs to be tackled, and where the opportunities are. In the university, we try to be ambitious about moving forward on all three of these agendas. We can really only do it effectively with partnerships that involve interested groups in the private sector, in the NGO sector, in the government sector, in Washington, in Sacramento, and around the world. So thank you for joining us here today. Today's session is part of an ongoing series to advance this broader agenda. The next session we have will be on January 30th, focused on climate adaptation. We're especially fortunate today to be able to talk about clean energy, opportunities for clean energy in terms of increasing national security, increasing energy security, creating economic opportunities, and I think it'll be a really exciting session. The format for today's session is going to be mainly structured as a dialogue. There'll be brief opening comments from each of the presenters, followed by a long period for each of you to ask your questions and explore the issues that you find to be most relevant in this area. In order to have the dialogue go in an efficient way, the most important thing is when you request the floor, please wait for a microphone so that everybody can hear the question and we can all participate in the dialogue in a constructive way. As I leave the stage, I just want to thank each of the presenters, and I want to introduce Varun Sivaram, who will moderate today's session. Varun is an especially important person in the Stanford Woods Institute and the Stanford Precourt Institute. He's on the advisory boards of each, where he really adds great value. His perspective is richly informed by his experience as the Douglas Dillon Fellow at the Council on Foreign Relations and by extensive experience in the government, in consulting, and in academics. Varun is and also an incredibly important source of energy with the advisory councils of both of the institutes that he participates in. He reduces the average age of the advisory council by more than a decade, which is single-handedly an amazing contribution. But the energy and perspective that Varun contributes are valuable much beyond reducing the average age. It's the perspective of utilizing the technologies, utilizing the knowledge base in order to make fundamental progress. And I was thrilled to see Varun named just last week to Fortune magazine's 30 Under 30 recognition in the area of law and policy. And that gives you an indication of the kind of impact that he's having in his career. So Varun, the program's yours.
Good afternoon, and thanks everyone for joining us. I am thrilled to be here. I really appreciate the invitation, and let me say thank you to Chris first. We're all so excited that Chris has taken over as director of the Woods Institute. He brings a tremendous amount of experience. As many of you know, Chris Field is one of the top and most important scientists behind the IPCC process, and I think Stanford is very, very lucky to have him leading the Woods Institute at a time when climate change in particular is one of the most important global issues we face. More importantly than that, though, Chris was actually my most popular guest at the Council on Foreign Relations. And so for that, I thank you, Chris. I'm thrilled to be here to talk about a topic that's near and dear, clean energy innovation. You know, a few weeks ago, I was at an event with my colleague, David Hart, who's over there. And I was trying to explain, you know, there is a silver lining here with the incoming new administration. As I got off stage, somebody asked me, is there really a silver lining to an acid rain cloud? And I said, you know what? There is a silver lining here. And the silver lining is energy innovation could really take center stage under the administration of President-elect Donald Trump. And I think that's because energy innovation speaks to some of the issues most prominent on the campaign trail. For example, the United States is looking to rebuild and rejuvenate its advanced manufacturing industries. We're in a race with countries like China over a $300 billion clean energy market that is expanding rapidly. And it's new technologies that are going to allow us to do that. And it's universities like Stanford and the researchers you're going to hear from today who would be on the leading edge of that sort of transformation. That's what I think the silver lining here is. And that's why I'm so excited that energy innovation could take center stage over the next several years. I will say it is my personal hope that some of the advances that we've seen under this administration on energy innovation are maintained and built upon. I think the Obama administration has made great progress in developing institutions. For example, the Advanced Research Projects Agency in Energy, ARPA-E, founded, by the way, by co-director of the Precourt Institute, Varun Majumdar, who wasn't able to be with us today. There have been great strides, and the United States' leadership in concluding Mission Innovation, a commitment to double U.S. research and development funding. Those are all very important steps, and I hope that the next administration will take them and run with it. With that, I'd love to introduce our three panelists so we can kick off a conversation about energy innovation. To my right, well, actually, let me start all the way in order of their opening remarks. Let me start with John Dabiri. He's a professor in civil and environmental engineering as well as mechanical engineering. I was trying to figure out which awards to cite for John, and I literally could not make a decision here. John is a MacArthur Genius grantee. He was Popular Science named him one of its brilliant 10. He's MIT's 35 under 35. He told me that he recently got to meet President Obama because of the Presidential Early Career Fellowship. His research is in bio-inspired propulsion, bio-inspired wind, the intersection of biology, science and technology, and energy and environment. I'm super excited to hear from John about his research. To John's left is Mike McGee. Mike, I am excited to say, was one of my professors. I took his class on solar cells, and Mike helped launch my career in solar cells. I'm very grateful to him, and he's been a mentor and an inspiration. Mike is a professor in material science and engineering. He's also a senior fellow at the Precourt Institute for Energy. And his research interests are in perovskite solar power, which is one of the discoveries that has just rocked the scientific community. So Mike is an absolute rock star scientist. As I mentioned, he teaches courses on nanotechnology and solar cells. And his former students have started over 10 companies, many of which Mike is currently involved in. And then finally, to Mike's left, is Sally Benson. And Sally is the co-director of the Precourt Institute on Energy. I'm really honored that I get to join her board meetings, and her leadership has been terrific. Sally is the reason that Stanford was able to raise over $200 million for the GSEP program, a partnership with private industry that allows Stanford to fund so much of its important research. And Sally's at the cutting edge of building newer, modern partnerships with the private sector. I think that's super important in the future of academic research. She also is a professor in the Energy Resources and Engineering department, and along with directing the Precourt Institute as a senior fellow, her research interests are in geological storage of carbon dioxide, subsurface characterization and monitoring, as well as low carbon energy systems. And she has a really elegant paper out recently on the hydrogen economy versus an economy based on batteries and electric vehicles. And so with that, let me finally mention, I was just glancing down Sally's bio and noticed, oh my gosh, the Nobel Peace Prize, because Sally was one of the scientists, along with Chris, who received the Nobel Peace Prize for their work on the IPCC. So we have an amazingly distinguished panel. I'm so honored to be here. And let me kick it off starting with John. Oh, just to tell you how the format will go. We're going to have each of our speakers give 5 to 7 minutes of opening remarks. Then we're going to have a moderated discussion among them as we drill into both their research interests and the implications given our new administration and Congress here in DC. And finally, we'd love to take questions from the audience. So with that, let me start with John. John, we're thrilled to have you.
Thank you. Thanks for having me. And I thought I would start us off by talking about an area of renewable energy that actually doesn't get a lot of attention, but that I think could have a significant effect on job creation and innovation for the next 5 or 10 years, and that's distributed wind energy generation. Now, this is different from the wind energy you're used to seeing, the very large turbines that are typically sited in just a few locations around the country, and then that energy is sent over long distances to the end users. In distributed wind energy, we're looking at much smaller devices that are distributed over a much broader geographical area, in many cases closer to the end user, and that has a lot of potential advantages for both the cost of energy and also its versatility. Now, you might ask, why hasn't this been done yet? And part of the challenge has been we haven't had the ability to identify the locations where renewable energy exists in more complex environments, like downtown Washington, D.C., for example. And so if you look at solar energy as a counterexample, I can right now log on to Project Sunrun, a project by Google, or Solar City, and I can identify on the roof of this building what the solar energy is here, how much it would cost to install the panels, what my return on investment would be. I can't do that for wind energy here right now, and it's in part because the physics are a bit more complex for the wind energy at this location versus the solar resource. But as these new technologies have been coming online, we now have that capability. And so I see this as opening up a lot of opportunities both on the practical side in job creation and also in innovation. So on the job creation side, the fact that your resource is distributed more broadly, it means you don't have to move to the nearest mine or the nearest well in order to take advantage of that energy boom. And so while this energy boom can occur in the Dakotas and in the Gulf of Mexico, it can also occur in the Southeast, the Northeast, California, anywhere where this wind resource is located. Now, the other important benefit here is in innovation because the barriers to entry are much lower. In conventional wind energy, if I wanted to prototype a 1 megawatt wind turbine, let's say, I need about $10 million to do that. And so that automatically limits the types of people, the groups that can become involved. By contrast, these smaller wind turbines that we're looking at can be prototyped for $10,000 or $20,000. And so at that much lower cost of entry, I think we can see a lot of interesting innovation in this space, both in terms of the designs of the turbines, but also how they're manufactured. As Varun said, additive manufacturing, for example, is an area that is very exciting. 3D printing our technology. That's something you simply can't do for a 130-foot-long blade, but you could do for blades that are a few feet long, as in the case of these types of turbines. Now, I think when we talk about innovation, we have to remember that in the United States, our most valuable asset is the people. We see this at Stanford, the students that we're able to educate. And they have been attracted to this in the same way that the Apollo mission inspired a generation to pursue science, the same way that today computer science has really revolutionized the way that kids think about what they're going to do when they get older. For us, we've seen that our students are interested in a variety of potential applications, everything from energy security, the fact that if I have an energy system that's distributed, it becomes more robust and resilient. It's relatively straightforward to take down one wind turbine that's very large. If they're distributed over a network of thousands of them, it becomes a different task. I think in addition to energy security, energy poverty is something that our students think a lot about, both in the US and abroad. Now, usually we think of energy poverty as a rural village in India that doesn't have access to electricity, and that is certainly an important application. But we must remember that even in Alaska, we have citizens in the United States who are paying 70, 80, 90 cents a kilowatt hour for their energy because they're using diesel fuel, and that fuel has to be flown into these villages. And so we're working with a couple of villages up there right now, installing these smaller wind turbines and displacing some of their consumption of diesel fuel, and at the same time putting them on a path towards sustainability. And the other area, I know, politically it gets a bit trickier going forward, is climate. Students want to have an impact in climate, and they see these technologies as a way to have an impact there. Now, what do we need to do to move this field forward? I think it maybe is the obvious thing of supporting basic research, but I think distributed wind energy has a unique challenge because the existing players in the space, whether it's GE as a manufacturer, NextEra as an operator of wind farms, they've spent hundreds of millions of dollars and decades on an existing paradigm of centralized generation. And so there isn't a lot of appetite right now in that space to invest in innovation in something that could be orthogonal to what they're currently doing. And so I think it is going to be important for the federal government to support this new type of investment. Also attracting other players in private industry that maybe haven't been in the energy sector, whether that's defense, it could be other technology companies that know how to do the manufacturing. One of the really exciting opportunities I see here is that because these systems are much simpler, a conventional wind turbine has about 8,000 components. These smaller turbines have a dozen or two. That allows a much broader set of manufacturers to play in this space, and I think that that's a real opportunity that we could take advantage of. And then lastly, and this will maybe segue into what Mike will talk about, is the opportunity for integration. So wind energy can very much be integrated with conventional fossil fuels, integrated with solar energy, integrated with other new forms of renewable generation. And so I think what we're going to see in this distributed context is a variety of different manifestations of the technology. In our Alaskan village, it's a combination of hydrokinetic and diesel and wind. In our project in Southern California, it's solar and wind. Each of these different areas you can imagine being tailored to this technology in ways that are really exciting. And so we'll continue the conversation here in the next couple of hours, but I'll let Mike take over and talk about integration as well.
Thanks. Mike, go ahead.
Sure. I've been working on solar cells for about 17 years now. And when I started, there was very little interest in the subject. Certainly if you lived in Silicon Valley and you worked in semiconductors, most people would work on computer chips. But I saw the long-term need and thought it was a very exciting area. Like John was saying, there's a lot of students really excited to work on renewable energy. And so it's been really rewarding to see the success that the solar industry has finally started to have over the last 5 years. The industry is growing by about 30 to 40% every year, and the costs have of the solar panels have dropped by more than a factor of 10 in the last 6 or 7 years, and now we have a situation where depending on where you live, it can be cheaper to get your electricity from solar cells. So in California and Hawaii would be another good example, where electricity is relatively expensive and there's a lot of sunshine. It now is more economical for people to get their electricity from solar cells. And one of the things I find interesting about my job is there are people who tell me I'm wasting my time because solar will never make it. And then there are people who tell me I'm wasting my time because it already has made it. And the silicon panels we have are good enough. Fortunately, there are people who think I'm working on great problems. Let me explain why my group is continuing to work on solar, and we still think there are important research challenges. Solar is really just on the cusp. Like I said earlier, it's competitive in some markets, but not all. It still needs to get about 2 or 3 times more cost effective. And When you analyze it, you realize that right now less than half of the cost is in the panel. The rest is in installing it, and also some of it's in the permitting process. And what that means for people like me who design and make the panels, even if half the cost is in the installation, there is something we can do. If we make the panels more efficient, then indirectly that cuts down on the installation costs. And one of the ways there's a couple scenarios. In some cases, you just simply install fewer panels if they're more efficient. But in another situation, imagine that you're going to cover a rooftop, and whether you put on a dozen panels that are 16% efficient or you put on a dozen panels that are 25% efficient, your installation costs are exactly the same. But if you put on the more efficient panels, you're going to be getting a lot more power out of that installation, and so overall you have a more cost-effective system. And so that's why it's all about efficiency now. We have to find ways to raise the efficiency without increasing the costs, or at least with minimal increase in the costs. And a few years ago, there was a real breakthrough, and Varun was a part of this as a graduate student at Oxford. We have a new material, we call it a perovskite, and one thing that's nice about it, we can just print it. And if we want, we can make flexible solar cells. We could take something that looks kind of like a newspaper printing press, but we can print solar cells instead. And one direction you might go with that is ultra low cost panels, and they might be flexible and you might just roll them out on rooftops. But another direction is that you can print these cells right on top of silicon cells. And the top cell can be designed to harvest the high energy photons in the solar spectrum, and that cell can generate a high voltage. And then the silicon is better at harvesting the lower energy photons. And without getting too technical, two solar cells that harvest different parts of the spectrum can do better than just one. And we can raise the efficiency from where it is today, 16 to 20%, up into the 25 to 30% zone. And because we can print that top solar cell, there's very little addition in cost. And a lot of the cost is in the packaging, and we don't change that. You know, we're not adding any extra packaging. We're just sticking in a couple of low-cost layers that we can print and significantly raising the efficiency. And that would be why I think we need to continue research. I think we can make the product a lot better. And you know, if you look at other industries, it's kind of ridiculous to think that as soon as you have cars working, you stop doing research on them, or as soon as you have, you know, if we had stopped where the Wright brothers were with airplanes, you know, we wouldn't have the Dreamliner 787. So I see it the other way. Now that it's clear that the solar industry is going to make it, we know with confidence that we should do the research to make improvements and keep raising the efficiency, make them cheaper, make them look more attractive, make them more flexible, you know, integrate them right into buildings so that you might not even notice that there are solar cells up on the roof. So there, I'll stop there, and I look forward to taking your questions.
Thanks, Mike. Sally?
Okay, all right, well, I'm going to do something kind of different. So what I'm going to do is offer a perspective about energy R&D in the context of 3 time frames. I'll talk about things that are here today, that are the results of the fruition of decades of research in energy technologies. I'll talk about things that are coming soon, and then I'll talk about things that are on the horizon. And so I think the lineup was perfect to hear about wind and solar, and in fact that there's really been a revolution in both of these technologies in the right place at the right time. These can be the low-cost energy providers, electricity providers. There's been some really stunning news recently about solar installations, utility-scale solar installations in Mexico and in the Middle East on the order of 3 cents a kilowatt hour. That's undoubtedly the low-cost provider. And again, in many places, wind is the same. And because this has become visible really only in the past decade or so, I think a lot of us tend to think that these are, new when they kind of came, like a flash in a pan. But in reality, the research started on these in the 1970s in earnest when we had the first energy crisis. And these were really motivated by energy security. There was a real concern that we were relying on others for our energy, which was simply far too important. It was disruptive, it was expensive, and hence we began this first round of innovation. So we think back to the 70s, and here we are in 2016, and we're reaping the fruits of this, incredibly beneficial investment that, clearly was on a rocky road, but nevertheless came to fruition. And so if you think back, like if you ask somebody in the late 1970s, you say, well, what about if you could have an energy source where the source of the fuel is free, that we're going to create 770,000 jobs in 2016, and that and it's available everywhere, and with continuing improvements in technologies, even further cheaper. So I think everybody would argue that, or say that this was a terrific investment. There's another one that is often surrounded by some controversy, which is natural gas. And again, in the 1970s, there were real concerns that we were running out of oil and gas, and the government decided together with private industry to invest in a new generation of technologies, particularly horizontal drilling and hydraulic fracturing. And actually, the first project I ever worked on in my career at a national laboratory was hydraulic fracturing for geothermal wells, believe it or not. So again, through R&D at the labs and universities and in the private sector, eventually we learned how to hydraulically fracture rocks with horizontal wells, and found out that rocks we formerly thought were what we called cap rocks or seals. That's what trapped the oil and gas from coming out, that all of a sudden we learned that we could actually produce tremendous amounts of natural gas and oil from these, fundamentally changing the United States' position with regard to energy independence. And in fact, one could argue that much of the low oil prices around the world were driven by the US boom resulting from this. So natural gas in the United States is incredibly inexpensive. It also has environmental benefits, that it's about 50% less CO2 emissions for every unit of electricity that's produced. Also hugely beneficial is through the development of gas turbine technology. We can now produce electricity with 60% efficiency. That's astonishing. That's about double the efficiency of the typical coal plant in the United States. So again, huge benefits from this investment. And again, was this a rocky road? Were there periods when we felt it was hopeless? Yes, absolutely. But perseverance ultimately paid off, really due to human ingenuity. And the consequences of this is that we've seen an enormous shift from coal to natural gas, driven by price in the United States, which has had the combined benefits of a more efficient generation, plus being able to reduce emissions. So the United States actually reached peak emissions, CO2 emissions, in about 2006, due in part to this natural gas boom. So that's three amazing success stories across a different regime. So what I want to talk about now is what's next. What are things that are coming soon? And I really think the key issue has to do with energy systems integration. So you've heard we have wind power, we have solar power. Again, the fuel is free. These are creating lots of jobs. But it's a challenge, because unlike traditional generation, where the system operator can call up a power plant operator and say, well, we need you to turn on your plant at 6 o'clock in the morning, that doesn't happen with wind and solar. They're variable generation. So we can certainly integrate a little bit into the electric grid, but as we try to integrate more, it gets more and more challenging. So the system operators are developing a new suite of tools. Clearly markets, real-time markets, energy imbalance markets, which allow more participants who can respond rapidly to contribute to the system, is important. the ability to do demand-side management, to not only control the generation, but to actually control how much we're using. And key to that in this next generation of technologies is going to be the use of information technology to gather a tremendous amount of information about the state of the grid, use that information to control, again, both generation and demand to make this integration of these resources more possible. So we live in California, and California has embarked on an experiment to radically increase the amount of renewable generation that we have. Our goal is 33% by 2020, 50% by 2030, and we're well on our way to do that. But I will say that the reason we have been able to be so successful is because, again, natural gas generation. We have a tremendous amount of solar energy on the grid. We have about 10 gigawatts of utility scale solar that we can use to generate electricity today. And when the sun goes down, that means we drop, 10 gigawatts over a relatively short time. What's making the difference is natural gas, which you can rapidly ramp up these turbines. So a little bit more on another integration that's very important and a technology that's coming soon are electric vehicles. All the major auto manufacturers now have electric vehicle offerings. They're coming down in price. I think the GM, the Bolt is very, very exciting that they're going to be selling this for about $37,000. It has a range of about 230 miles. That is the beginning of a revolution. Now, certainly we all love our Teslas, but most people can't afford a Tesla. But of course, we do have the next model of Tesla coming along soon, too. So that in and of itself is a real game changer that's coming soon, but also creates both new opportunities and challenges for energy systems integration. I'd just like to wrap up with a little bit about what's on the horizon, that ultimately, as we fully take advantage of the renewable resources and low carbon natural gas we have today, we fully develop the energy integration tools and technologies, we're going to need to do more because ultimately we need to decarbonize, we need to get to net zero carbon emissions, and technologies like carbon capture and storage are going to be absolutely crucial to being able to achieve this. There are many studies that show that not only does it make it much easier to fully decarbonize the energy system, but it also shows that by incorporating carbon capture and storage, it will be the lower cost option. So I'd just like to wrap up, saying that R&D has been incredibly successful in transforming our energy system, making us more secure, having the possibility of lower cost energy, and that we definitely need to keep this up, not only to sustain progress in those platform technologies which are now available, but we also need to think about what are going to be the revolutions 30 years from now, and we need to keep a strong investment in that fundamental underpinnings for the next generation energy systems as well.
Thank you, Sally. I'd love to jump off of a couple things you just said. You pointed out that a lot of the many technology revolutions have actually been in the fossil fuel, oil and gas industry. And you've pointed out that the oil and gas industry, for example, through natural gas turbines, are one of the reasons that we're able to have revolutions like the wind and solar revolution. So I wonder if you could comment a little bit about, as the world moves forward inexorably toward decarbonization, or so we hope, what is the role for fossil fuel companies to play in that world?
Mm-hmm. Yeah, I mean, I personally think they have an incredibly important role. They know about scale. They know about large-scale investments. They know about risk management. And when we talk about the energy system, those things are incredibly important. So talk about sort of a time sequence. I think in the short term, natural gas is going to be hugely beneficial to the energy system. It can displace coal, which again has big environmental benefits, actually, not only in in CO2 emissions, but traditional pollutants. So I think for the short term, helping not only to make more natural gas available in the United States, but to make that available around the world. There are many shale gas resources around the world. They may not be exactly the same as the ones in the United States. I think also creating a global LNG market, a robust LNG market that can produce predictable prices will be hugely beneficial. So, but again, that's not enough. That's just the very beginning. So then what do you do next? Well, imagine that you have a power plant, the natural gas power plant. You've got a gas pipeline going from the gas field to that pipeline, to that power plant. Why shouldn't we also have a pipeline coming back filled with CO2? You know, follow that same route, come back, and you can take that CO2, you can put it into the natural gas reservoir, you could put it into a saline reservoir aquifer. So I think the oil and gas industry needs to start thinking about not only offering low carbon products, but no carbon products, and CCS will be a crucial part to that. I think they also need to start thinking about the transportation system, and certainly electrification of vehicles with a no carbon or low carbon grid is a step. But I think we also need to think about heavy duty transportation. This is expected to grow globally. And I think there's a big opportunity for hydrogen or hydrogen methane hybrids that either use internal combustion engines or possibly fuel cells. And again, hydrogen can be produced as a decarbonized product from natural gas as the feedstock by carbon capture and sequestration. One can also imagine if they've already got this hydrogen infrastructure that's providing this no carbon fuel, maybe they start seriously thinking about taking renewables and producing hydrogen and integrating that in. So I think that's in the midterm. I think they could also offer their services to help the coal industry develop the technology, get more experience with carbon capture and storage technology. That's probably not going to be a main line of business for them, but they can de-risk that technology. And then in the really long run, there's a tremendous amount of interest in the possibility of using CO2 for something useful beyond enhanced oil recovery. Actually, I didn't say that. Certainly, the oil industry can also help develop CCS through the use of CO2 enhanced oil recovery. But again, CO2 utilization broadly, if we go to all the effort to separate the CO2, we've spent all this money, is there something useful we can do with it? There's been a lot of interest in making fuels or other green chemicals with CO2. That's a very, very hard problem. But I think, again, if that is going to be done, I think that industry is the one that's most capable of pulling it off.
Thanks, Sally. I'll add that, other potential applications for the utilization of CO2 include cement curing, using it to create carbon fiber. I mean, there's a lot of things we can do with it. Mike, I'd love to riff off something you said, which I thought was hilarious. People have been telling you that you shouldn't be doing what you're doing because solar won't succeed, and now you shouldn't be doing what you're doing because solar has already succeeded too much. That's very interesting, and in fact, that is not a trivial statement. That, in fact, Lazard's December 2016 projection has both solar and wind, John, at less than 5 cents a kilowatt hour, and I think those numbers may have been unsubsidized in some parts of the country, with significant runway for costs to go down using existing technology, silicon for solar and horizontal axis wind turbines with 3 blades for wind. And so a lot of people do think that the path forward is with existing technologies. We have what we need. But you guys made compelling arguments for why your products are both superior in existing use cases and also offer brand new use cases that the existing technologies can't conquer. So I wonder if you guys might be willing to talk a little more about what it would take to get your technologies into the market and what sorts of barriers you face to do so.
I'll go first.
You want to start off?
Right. Yeah, there was a key number I forgot to say earlier. Just a few weeks ago, right before the Christmas break, my research group put the perovskite solar cell on top of silicon, and we took a 21% silicon solar cell and raised the efficiency up to 25.3. So, we're taking this product that is about a $50 billion per year industry, and we're making it 20% better in a way that barely raises the cost. And we see a pathway to getting the efficiency to about 30%. So I think it's a very, very exciting opportunity. I have started a company called Iris PV to commercialize this technology. Despite the promise, we are having a very difficult time raising funds to do this. A lot of investments in solar companies from about the 2005 to 2008 period did not do well. There were about 250 startups, and right now there are about 7 or 8 solar cell companies that have the whole market. And I mean, that's just the way it is. There was a competition, and there were 7 or 8 winners, and lots of other companies, their approach turned out, not to be competitive with silicon. And in my personal opinion, there was way too much investment at that time. The vast majority of the time when investors asked me for my opinion, I told them that startup does not have good technology and you should not be investing in it. But there was such a rush to invest that they were investing anyway. And now we've swung too far the other way. And the perovskites have given us a truly very exciting opportunity. But the herd mentality right now is against investing in solar. And I think that they're making mistakes. And so now we have a situation where at the university lab, we're going much further down the applied direction than you would normally see. Like for example, we're doing long-term stability tests in my lab. Normally you would hand that off and a company would do that. But I think it's good that we're doing it and showing we're just dropping the risk more and more, so that at some point investors will say, wow, there's hardly any risk left at all. This is almost a sure thing. That may be either that or investors need to be willing to take a little bit of risk, also see the social value. But right now in Silicon Valley, they're pretty excited about apps and stuff on your smartphone where they feel like they can make billions very quickly.
John?
Yeah, I think wind energy is in a challenging place, in part because of this moniker of being mature. When you're a teenager, I guess that's a compliment. But in technology, it means, okay, we don't need to invest in you anymore. And I think what we've seen is that it's true to, we can get very low costs for commercial wind. But right now, last year, for example, 4 or 5% of our electricity was generated from wind. And the question is, can we get that to 20%, 25%? And you run into some very practical challenges. For instance, expanding the map of locations where you can actually generate energy without running into environmental concerns with bird and bat impacts, running into issues with the FAA and the military with radar impacts. When you start to cross off these different areas, places near where people live and work because they don't want to see the turbines, you realize that the locations that we can actually expand into are actually relatively limited. And so because of that, to your question of how can we expand these new technologies, I think it's by demonstrating that we can then reopen this map of locations where wind can be effectively deployed. In the case of birds and bats, for example, we've been studying these vertical axis wind turbines. Imagine the blades like a carousel rotating on a vertical axis. We've been studying them at our field site in Southern California for 6 or 7 years now and have not had a single bird or bat strike. Part of that's because they're closer to the ground, so birds typically are flying overhead, but also the visual signature is different from what you would see from a very rapidly rotating blade. So that becomes a potential opportunity to install turbines in sensitive locations. When they're smaller, the visual signature is reduced, the acoustic signature, the radar signature, all of those things that indicate the presence of this technology are much smaller. And so again, it opens up a lot of opportunities for generation. What we found is that we can also look at repowering existing sites. So Northern California, for example, home to some of the earliest wind farms and also some of the best wind resources in the world. But if you go to the Altamont Pass, where those turbines are located, you'll find many of the turbines in the best locations are quite old, and it's not economically feasible to replace them with the more modern turbines yet. With this new technology we've been developing, you can actually repower the site by leaving the old turbines there and simply installing these between them. You can't do that with conventional turbines because each wind turbine of the conventional style generates a wake, as we call it, a choppy air behind each turbine. And so you need to spread them very far apart from one another in order to maintain performance. You don't need to do that with these vertical axis wind turbines because of the different wake signature. So we aim to piggyback off of existing technology by augmenting performance in existing sites, and then also demonstrating the ability to generate energy in places where the current technology simply can't go.
You know, one of the, and those are super helpful answers. I think the incremental approach for both of you, in Mike's case, to put a perovskite on top of an existing product, a silicon panel, that's a great incremental way to get into the market rather than changing the entire paradigm. Similarly, repowering farms is another way of taking existing infrastructure and being incremental on top of it. I wonder, in the clean energy space compared with other spaces, the level of corporate investment in innovation is sometimes underwhelming. You know, in the Silicon Valley boom and bust that you talked about, Mike, one of the reasons that companies, didn't manage to post good returns to pay back their VCs was because corporations weren't acquiring them at the same rate as they might in, say, the life sciences sector. I wonder for both of you, and perhaps Sally, you might chime in as well, what would it take to get large companies, in your case GE, in your case, this could be Chinese solar companies or US solar companies, what would it take to get large companies to invest strategically in brand new technologies that might be altering the paradigm that they are already part of?
This is a question that we've posed directly to companies like GE, Siemens, Vestas, and it comes down to technical risk. I mean, these companies, again, have invested hundreds of millions of dollars, decades in developing the three-bladed turbine that you all see, and so they have something that works well enough to meet a bottom line. What we found, and this goes back to a comment Mike made earlier, is that in the university, we're having to take on some of the duties of resolving that technical risk for them. So for example, in the case of these vertical axis wind turbines, we're deploying them in this village in Alaska, at a research site in Southern California, and going through the process of working out all the kinks of how do you improve reliability, predictability of performance. And so I think basically what they're looking for is a product that has been de-risked by the university or by some other entity. For us, we feel that it's important enough of a technology that we're willing to do that, but it's not cheap. And we're fortunate that Stanford and some of our partners, nonprofits and federal government as well, are willing to take on some of that load. But they're only willing to do that to a certain limit. And at some point, we do need the major companies to step in as well.
Sally, what are you seeing from your company partners?
Right.
What appeals?
Yeah, I think that's a really great question. We've had the opportunity to work with a number of major companies over the years. As you mentioned, the Global Climate and Energy Project had an investment of more than $225 million. And I will say, it was absolutely visionary in 2002 to have this group of companies come together to collectively invest in a portfolio of technologies that would be foundational to this next generation of energy technologies. And we didn't do any work on wind, but because you never told us about you, we didn't learn about you till later. But we did make a lot of investment in solar panels and so forth, and some of the work that Mike has been talking about was supported by that. So that was a very positive experience, very fundamental. But I will say that my interactions with the companies have made me realize how challenging their environment is, that with quarterly earnings statements and the relentless drive to reduce costs so that they can remain competitive in this global environment makes it very, very difficult for them to make these investments. And in particular, if you look at many companies that, again, many decades ago, they had large and robust, R&D departments. If you look at Bell Labs as, the ultimate of all these, In the United States, we fundamentally backed away from doing that, and very few companies really have the capacity for this kind of more transformational research. So I don't know how we solve that problem, but certainly reprioritizing the idea that you know, great companies, great American companies, are not only investing in the here and now, but are investing for the long term, I think as a change of mindset would be incredibly important in doing that. But in the meantime, I think just what you've heard is that de-risking these technologies, not only to the point where the technical risk is low, but the productized thing can be seen and envisioned. You know, I'll just give a short anecdote. So this year at our Global Climate and Energy Project Symposium, we had a technology showcase where many of the students and faculty who'd worked with the program who had startups came back and sort of showed off the thing. Everybody loved it. It was like, wow, this is the most fantastic thing. And what was fundamentally different, not that new science had been accomplished necessarily at that, but they'd been productized. People could imagine, there was the pitch. Here's what I'm going to sell. And so that level of de-risking, I think at least at this moment in time, for a very stressed group of industries, is what seems to be most successful. But I think in the long term, you know, a change of heart, a change of mindset is going to be really important to keep our industries healthy.
So you just mentioned ways to get great American companies to once again, or to increase their efforts here in the United States, and that's a theme that we have heard on the campaign trail and recently from the president-elect. Ways to get great American companies to build things at home. Now, John, you mentioned early on that these vertical axis wind turbines, sorry, I'm like conditionally, conditioned to say horizontal, it's vertical axis, that these turbines could be created through additive manufacturing. Mike, I know that your group works on pretty cool manufacturing techniques, but in both of your cases, both of your techniques can be highly automated. It's actually hard to create jobs doing additive manufacturing or a printing press type approach. So I wonder, what's it going to take for these technologies to create jobs, first of all, in the United States, and to create human jobs and not robot jobs?
It's a tough question. I grew up in Toledo, Ohio. My dad worked for an auto company doing drafting that now is done by a computer in an automated sense. And so I certainly appreciate the fact that the trend toward automation has real impacts on people's lives. In the case of these wind turbines, I think it's also the case that, as you say, with additive manufacturing, some of this can be automated. Now, there is, I think, a space for jobs around the systems that create the systems, if you will. I would say that the thing that still is unsolved is how do you train the existing workers for that? So our Stanford students, the students at the University of Toledo, which is our home, go Rockets, anyone? I don't know. From the Toledo area. They can learn these skills to develop the next additive manufacturing system. Can my father, who worked in the factory for 30 years, do it? I don't know. I think there is a challenge for that segment of our population in bringing jobs back. I think there's frankly been an overpromising of bringing those jobs back. But I do think for the younger generation, it'll be learning the technologies that allow us to do that creation. And then, as Sally mentioned earlier, the information technology aspect of these technologies. When I have 10,000 of these vertical axis turbines, and I want to optimize their operation so that in DC versus Baltimore versus somewhere else, the energy they're generating is somehow conditioned, or using information about wind patterns that are coming to the front of the city and using that predictively to optimize the turbines further downwind. These are all technologies that still need to be innovated and I think can develop jobs, but it's a different type of job than the ones that have been lost over the past couple of decades. I don't think those jobs are coming back.
Yeah. Mike or Sally on that?
I mean, some of what he's saying there is going to be true for all industries. I mean, all factories are going to be more and more automated. That's just how it's going to be. But, some jobs is better than no jobs, and it's still good to manufacture in the United States. And China has done very well in the solar industry, but I think a good chunk of the industry could come back to the United States. And it turns out that the amount of money you save by using lower cost labor in China is about the same as what you would save if you do it here on shipping costs. And so there really isn't a benefit to doing it in China. The reason it's happening in China is simply the Chinese government's willingness to provide low interest loans. You know, they've provided about $50 billion in low interest loans, and that's really just about the only reason that the industry has taken off in China. And so if we were to develop the right business environment, I think that the solar industry could be here. And a conservative estimate is that only about 20% of the factories we will eventually need have already been made. So at least 80% of the factories have not yet been built, and they could be here.
Just to put a finer point on it, jobs are currently in China because they have government support, but also the industry is there presumably because if we were making more innovative products, it would be easier for the industries to be here. Am I right in saying that? If cutting edge technology were successfully commercialized, companies would be more likely to set down roots here in the United States.
Yeah, and I think most people in Silicon Valley would agree that when we're putting out a really high-tech product, there are a lot of benefits to having the factory nearby so that the highly skilled PhDs can go back and forth between the R&D facility and the factory as needed. There are always going to be problems when you're getting a new factory going, and it's good to be able to send the people who invented the technology to the factory to diagnose and fix the problems. And it helps to talk to the people who run the factory to learn, what are things about the factory that could be made better to make the product better. So, we'd certainly prefer, to have the factories as close as possible to the research and development centers. And in the solar industry, I mean, we are seeing factories in upstate New York and Mississippi are two places that provided good tax incentives to, encourage companies to build their factories there.
One thing I would add just briefly is the operations and maintenance of conventional wind farms are where many of the jobs currently exist. So certainly the construction, the manufacturing, and installation is a component, but it's keeping them running for the next several decades. And so in that framework, you can imagine, and we've seen this in our Alaska project, training the local communities to take ownership of these energy generation facilities. It's a different paradigm from now where I flip the switch and I expect somebody somewhere else is doing the work so that my lights come on and I stay warm. In this village, the community themselves are the ones responsible for making sure these turbines remain operational, that they're able to perform as expected. And again, the simplicity of the turbine plays into the opportunity to take people who might only have high school education and be able to teach them how to diagnose what's wrong with this turbine and how to fix it. So I think there's another category of employment that has to do with the long-term operation of the systems that may actually be a bigger driver of jobs than the manufacturing of the turbines themselves.
Yeah, so I'd like to add, I think that's absolutely right. There's manufacturing, there's operations and maintenance, and then, as we think about in the new energy economy, the enormous amount of infrastructure investment in new transmission to put generating assets in the best locations, new pipelines to take, there are many parts of the country which have real shortages of natural gas, which create real stresses on the energy system. And the consequences, we keep using coal, which I think many could argue that from an environmental perspective is not the best option. And so in addition, the whole area of grid modernization, there's a tremendous amount. How do we put the sensing systems? How do we take advantage of the information to control the generating system? So again, those are jobs. Electric vehicle charging, all of the infrastructure that, and one can imagine many decades worth of jobs building that. I'll just add one anecdote that I think speaks to your point about operations and maintenance. I took a group of 12 students all over Southern California and Arizona and Nevada, and we visited a coal plant, a natural gas plant, wind turbines, desalination, solar PV, solar thermal systems. And we talked to a lot of the workers. Part of the class was to understand about jobs. And we ask people, well, are these good jobs? You make a good salary. Are you happy? Absolutely. They all love their jobs. And so at the solar plant, we say, well, what was your past job? Oh, I worked at the coal plant, okay? So, clearly these skills of mechanical, electrical, sort of systems operation are highly transferable. Similarly, we're over at the coal plant. What was your last job? Oh, I worked at the wind farm over there. So the fungibility of people, with these kind of skills, they're highly desired, they're very valuable and good paying jobs, and they can move around. So
I mean, I'll say that the top growing job in the United States is listed as wind farm technician. On top of that, there are more jobs created per capita from decentralized solar compared with centralized solar. And I presume the same relationship would hold for decentralized wind compared to centralized wind.
I would expect so. And again, I mentioned this in my earlier comments, the fact that you don't necessarily have to be co-located with the generating assets in this centralized location in Iowa or West Texas presents an opportunity for a wider cross-section of our society to participate in this energy boom.
Well, we are almost to the point where I'm going to open it up to audience questions, and so I'd love for everyone to start thinking about what you are going to ask. I'm just going to ask one or two final questions that I'd love to hear about. One is, you produced some great innovation briefs, and at the end of them, you provided policy recommendations. I wondered if each of you might discuss what policy recommendations you would make to the incoming administration, the incoming Congress, about what you most need to support energy innovation. Sally, would you like to start?
Sure. Yeah. So I'm only going to speak to R&D because that's what I really know about. So I think that I would have 4 priorities. The first one is carbon capture and storage. This is a technology which has been around for about 20 years. The majority of projects that have gotten started, of which there are relatively few, about 8 in the world today, have gone relatively well. However, the cost of capture is still too high to make it competitive with other decarbonization options. And second, there's the perception that CO2 storage it may be too much of a risk. So I think there's a tremendous opportunity to do more R&D, perhaps even focused on using oil and gas reservoirs as the primary opportunities for storage, again, to help de-risk the technology, and at the same time have the co-benefit of producing, increasing, domestic production of oil so that we can, again, decrease our dependence on other places. So that would be the first one. The second one is to really pursue advanced nuclear power. I think in a world where we want to get to zero carbon, maybe it's zero net carbon, but I'm not so convinced that negative carbon emissions are going to be realizable at much scale. I cannot, in the foreseeable future or fast enough, imagine being able to do this without CCS at a large scale and possibly nuclear being a crucial part of that. We need to, the U.S. is losing ground on nuclear power. I mean, we are far behind the other leaders. So I would, rethink that. Advanced reactors, small modular reactors, fail-safe reactors, where the kind of concerns that with our existing fleet would no longer be an issue. So that would be my second recommendation. The third one, I think, fundamental material, chemical, and geological sciences to sustain. What are we going to do 30 years from now? The world is not going to stop still. When we develop this whole next generation of platforms, we need the next generation after that, and I think that comes from the fundamental sciences. And then finally, I think that an overlooked but incredibly important effort is an energy systems analysis, energy systems integration analysis, because right now the energy system is so connected, it's very difficult to know what are good choices. And without really robust life cycle systems, techno-economic tools, it's very difficult to make good decisions. So I think that really trying to up that, get that from being an art to a science, documentation and clarity about inputs would be incredibly helpful in helping make us smarter about good choices.
Yeah, I'd like to maybe address a couple things that isn't what the three of us do, because that's what we've mostly talked about so far. I think everyone needs to be prepared for the electricity grid to change significantly. One of the reasons is our grid is getting really old, and it is going to start breaking down and need replacement anyway. But then the other is both wind and solar are intermittent, and we may need to be moving power around from where the sun or the wind is providing it to where it's needed. And we may need to build storage into the whole system. We may need to be able to set up the ability to shave peak load, like maybe turn down people's air conditioning at a moment when the grid can't provide the amount of power that people are asking for. So I think we have to prepare for all of those things. We didn't have a storage expert up here today, but I think storage is going to be incredibly important. If I look in the material science community that I'm in, sometimes there's a tendency for everyone to pile on to the most important problem. And maybe for the last 10 years, we saw that as solar, so everybody was doing solar. And then as solar started to succeed, there was both the funding agencies and people very rapidly shifting over to batteries. And that is important. I absolutely think we should be doing research on batteries. But I also hope that we don't have such a small pot of money available for funding that we have to dump research in some areas to pour it all into batteries right now. And I hope I made the case earlier that we still have important things to do in solar. And in general, energy is just so important that the country should be investing more than something like 5 to 10 billion per year. And just put that into perspective compared to what we spend, say, on defense. I think a very strong case can be made for raising and certainly not cutting the funding that's available for both the long-term research that Sally was talking about and the short-term. And because the companies no longer take as much risk, because they think about the next quarter instead of 3 to 5 years out, universities and national labs now need to do some more applied research. And so it's important for the funding to be available to do that.
I think we've seen in the Obama administration a very effective approach in leveraging other agencies outside of DOE and National Science Foundation. So for example, maybe a third of the research that we've been conducting has been through Department of Defense. They realize that their forward operating bases have a huge expense related to energy, both energy security, so think of the convoys that have to protect the fuel lines, for example, but even our bases here at home. So DoD is the largest single agency consumer of energy. And what the Obama administration has done is then to use that agency to leverage the implementation of new solar. In wind, the reason we got involved is that conventional wind turbines can be incompatible with helicopter operations, for example. For a forward operating base, it's hard to hide your location when a big wind turbine gets erected. And so they're looking into other ways to more surreptitiously extract wind energy. But those other agencies have been an important player in advancing renewables, and I'd like to see that continue going forward. The other thing is maybe a bit more mundane, but it's in the permitting of projects here in the US. And so we found, for example, in Northern California, wind turbine is sort of a bad word because of the environmental impact on birds that it's had in the area. And so we end up many times in a catch-22 where with the permitting agencies, they'll say, we won't allow you to install this new technology because of the potential negative impact on birds. But there's no way to prove that it won't have a negative impact unless you're able to install it somewhere. And so you end up stuck. And so I think it would be important to rethink how we evaluate new technologies in that context so that we can move these projects forward.
And And I should, on that note, permitting, I do want to recognize David Hayes all the way in the corner there, who, was an important force in the Obama administration for streamlining some of these permitting procedures on federal lands. So with that, I've got a million questions, but I'm going to save them. I would love to hear your questions. I'm going to take hands, but when I choose you, please just say who you are and with whom what your affiliation is, and wait for the mic. So let's start over there, gentleman in the blue suit. I think there are two gentlemen in blue suits, but yes.
Hi, my name is Umair Irfan. I'm a reporter with Energy and Environment News. With the incoming administration that has a very skeptical at best view on climate change and an Energy Department nominee who also shares that view, how do you make the case for clean energy innovation without climate change as the driver, particularly for something like CCS?
Well, I agree that that's a hard bet. I think that the opportunity for CO2 enhanced oil recovery is one of the motivators for doing that. I look at CCS as an insurance policy that because there's if I'm in California, there's a view that we can get all the power we need from wind, water, and sun, and that why do we need fossil fuels at all? Why do we need natural gas? Well, okay, say you're wrong, okay, and we do need natural gas. Well, if you have CCS, you can have natural gas. If you say, on the other hand, that you think all of this need for clean energy is a bunch of baloney, and you say, okay, let's just continue with fossil fuels as we do today. Well, but what if you're wrong? Well, if we're wrong, then if you've invested in CCS, you have something in your back pocket. So again, I think it's a good insurance policy for the two polar ends of the spectrum that at the end of the day can be helpful.
I think energy security is the maybe most effective approach because of the fact that it's bipartisan. We all understand the importance of securing our supply. And by adding these other modes of generation, especially if they can be manufactured here in the United States, we augment that. And then I would argue moving to the decentralized or distributed energy generation paradigm, you add a layer of resilience to the system that we don't have right now as well.
By the way, Umair had a great piece on mission innovation recently, and I think it's terrific that you're bringing up the issue. Let's go right here.
Thank you. Peggy Duxbury with East Potomac Partners. So what I heard is we're going to have a grid that's more integrated, more variable, and more distributed, and it's also aging. What role does the utility play in managing all this, since they're going to be central to the demand and they're the ones who have to operate it? And maybe don't talk about California utilities, but more traditionally vertically integrated utilities that aren't necessarily being pushed by state regulators to do this.
Who wants to kick off?
Who wants to kick off? Yeah. I'll say something. I mean, I think that the utility companies are really struggling right now because of the situation. What are they driven by? Reliability and low cost. And, this has been beat into the operating model and so forth. The way that they earn income on investments has made it, and the kind of investments they make have been limited. So I think that they've been put in a very, very difficult situation. I think we need to be more expansive on what they can invest in, what they can get cost recovery on. I think we should change the paradigm that they're operating under that will allow them to innovate. And we are seeing more innovation from certain regions and certain utility companies. So I think we really fundamentally need to re-examine it. I personally am very worried in places like California that we have done so much to marginalize the utility companies that they're kind of throwing up their hands and saying, okay, you don't want us to be concerned about reliability and so forth. You just want us to do this job. Well, okay. But who is really looking out for the stewardship of an infrastructure that is absolutely so crucial to modernity and to our way of life and to our security? And so I think we have work to do.
Let's take this side of the room. Yes, sir.
Terry Hill with the Passive House Institute. One of the things that from my point of view, there's too much stovepipe thinking going on. I liked your bringing in the security of the grid. That really seems to resonate here on the other side of the fence. And it's not being talked about enough as far as I'm concerned. But my question is, what role will direct current and direct current microgrids play in this future grid?
So I think in our research, we found that the implementation of these microgrids in Alaska, for example, where we have communities on these DC grids, it's allowed for a lot of flexibility in terms of the types of generation that can be accommodated. So as I mentioned, in that particular location, we have hydrokinetic generation because they're by the river. They have the conventional diesel facilities, and then you also have the wind turbine array as well. I would say one of the big challenges for a lot of these projects initially is knowing what's the right mix of different generating capabilities to put into play. And that has to go back to an earlier point I made about in wind, not really knowing quantitatively what the resource is at many of these places at a sort of micro level. And so I think as we improve our ability to make predictions about the resource, the wind resource in particular is what I'm thinking about, you can then use these DC microgrids in many more places around the country.
So when you say security, were you thinking of like cyber and physical security, or were you thinking about reliability?
Solar flares, reliability, breaking the distribution grid up into multiple little microgrids so that we've got a lot more diversity here than what we have today.
Right, yeah. I mean, I do think that cybersecurity and the electrical grid is, and its relation to physical security is an issue that will need much more attention. On one hand, you can argue that having a much more distributed system with much more intelligence and controls will make you more resilient and more reliable. On the other hand, one can imagine that every single device and every single piece of information it receives is a new vulnerability for both cyber and physical threats. I don't think that we know the answer to that. I think that that's a very important area for research, and a lot of attention should be paid to it.
And I think this does play into the previous question about utilities, because there's a quality assurance aspect that is very difficult to implement when you have these very decentralized sources of energy. And so we're going to have to think about some overarching system that's able to ensure that those individual units are operating as expected.
There's one more. Yep. The integration of the existing building stock. Who's thinking about, I think California is thinking about, what are we going to do with the existing building stock and what role will it play in the future grid? Like deep energy retrofits, for instance. Where are we going with that?
Thank you.
Again, that's not my area of expertise. I mean, it's hugely important. I mean, if you look at the efficiency of the U.S. on average compared to our European counterparts in terms of GDP or energy use per GDP, we have a lot of improvements we can make. I think unless we go after the existing building stock on deep retrofits, we're going to continue to pay a price for that. So it's and California is very, very active and aggressive in that regard.
I think I saw a hand right next to you. Yep.
Yes, hi, Andrew Patterson, Environmental Business International, Stanford Hum Bio, class of 79. I just checked, and perovskitevalley.com is available, if, Michael, you want to claim that. So questions about industrial restructuring given Silicon Valley. But we haven't heard any math yet on the wind and solar. Solar, Mike, the bear used to be $1 a watt. Where do perovskites take us? I mean, less than 20 cents a watt. And on wind, you talked about the advantages on energy being able to pack them closer together, but as you go down in scale with wind, you lose some of the energy density. So let's hear some math.
So yeah, silicon solar panel right now is actually all the way down to 42 cents per watt. And that'll probably go down to 30 to 35 in the coming years. And if we were to use perovskites by themselves, we think they might go to maybe 25 to 28 cents per watt. But what I'm more excited about is combining the technologies. And if you do that in this dollar per watt for the panel, I actually don't project it going lower. I project it just staying about the same. But then there's another metric that's more important called the levelized cost of electricity, because the dollar per watt is only telling you the upfront cost. And you have to look over the lifetime of the project, and then you also have to include installation costs. So when you've raised, if you can take two products and they're both 30 cents per watt, but one of them is much more efficient, then effectively that lowers your installation costs, and then you'll win on the levelized cost of electricity. Right.
How much time of sun time do you have?
Well, I don't know if we can increase that. I haven't solved that problem, but we can. It's the overall levelized cost of electricity that we're going after, and we're potentially looking at 30 to 50% reduction in that.
Yeah, so in winds right now, there's a few different figures of merit you can work with. If you're interested in the closeness of spacing, a conventional wind farm will generate somewhere in the 2 to 5 watts per square meter of power. So if I'm standing in the middle of that wind farm on a square meter of land, on average, I'm getting about 2 to 5 watts of power. What we've been doing over the past 5-6 years is studying these arrays of vertical axis wind turbines out in the field. They're 10 times smaller in terms of height. They generate 10 times more power per footprint. So in the 20 to 30 watts per square meter of power. And so you say, well, how does that work? Well, as you say, first of all, we have to compensate for the fact that we're lower to the ground. That turns out to be a significant challenge, because in wind energy, the power goes cubically with the wind speed. So if I double the wind, there's 8 times more power flux passing through the system. And so what we do is to take advantage of what we call collective behavior. Think of cyclists in the Tour de France, fish schooling in the ocean. You get a collective effect where the whole is greater than the sum of its parts. And so the flow past one of these wind turbines actually accelerates, and you can place another wind turbine at that location where the wind's maybe 5% higher in speed, but again, you have that cubic dependence on wind speed, so there's a lot more power at the next spot. And so we can optimize these systems to take advantage of that collective behavior that works for vertical axis wind turbines in a way that, for the reasons of the aerodynamics, doesn't work in the horizontal axis turbines. So that's how, at these much lower heights, you can still get meaningful power. Now, the catch there is that in most locations where you would want to install these smaller turbines, the wind is not only slower, but it's also more turbulent or choppy. And conventional wind turbines are not designed for that. They're designed in a wind tunnel with a uniform wind speed. The blade, the angle that the wind sees to the blades is constant. In these vertical axis wind turbines, the wind is more turbulent. And so one of the consequences of that is that the individual turbine efficiency is lower. But we see the efficiency as not necessarily being the most important feature. It's really how much energy can I get out for a given amount of cost that I put in, or long-term amortized cost. But those are some of the features that we think about in analyzing the system.
And John, just building off that, in some large wind farm cases, you're able to monetize the space between the wind turbines. For example, farmers can actually farm on the area between the large wind turbines. Do you guys model in losing that potential revenue stream if instead you pack the wind turbines really close together and no longer get land that's usable for other purposes?
Right, that's a good point. And so, in fact, the trade-off we see is a bit different. If you looked at a wind farm in Iowa or Indiana, although nominally you might say the entire area of that farm has the same wind speed, there's going to be slight variabilities in the wind, where over on this side of the farm it might be 10% higher than it is here. So the model is different. Instead of peppering the entire farm with these well-spaced out large wind turbines, we would simply concentrate all of these turbines on that patch that has the 10% higher wind speed in that area. And then you do have to ask the economic value of the wind energy versus the economic value of the crop. but it's only in that small space, and given the fact that you're able to generate 10 times more energy on a plot of land, it's a relatively small area that you're setting aside and dedicating to this. And then you're also getting the benefit of not having to transmit energy or wire up all of those turbines spread out over several thousand acres.
Thanks. Now I know that there are a bunch of people in my blind spot. I see you back there, and then we'll go to you.
My name's Kurt Renaud. I'm a business school alum. I don't think when matters really. And I start with Mike, a couple technology questions. As you're increasing efficiency of panels, what about hybrid thermal kinds of combinations as well? Can you tell us a little bit about developments in that area? And also I'm curious about ocean energy, if there's anything going on in there that you could tell us about. Thank you.
By hybrid thermal, do you mean that the device is absorbing sunlight and it's generating electricity and it's generating warm water as well? Right, that's one of the most popular questions I've gotten over the last 17 years. So it turns out you can't really do both, because solar cells do work better at lower temperatures, and so you would like to keep them, down at 70 to 90 degrees if you could, and it is if you used cooling water, yeah, the panels would work better. But then, let's say for your water heater, you're wanting your water at 120 to maybe 140 degrees Fahrenheit, and so either side would end up losing. If you picked some intermediary temperature, it's lukewarm water as far as your water heater is concerned, and it's actually kind of keeping your panel warm. For hot water to be valuable, it needs to be really hot. Like a lot of times, really steam is what you'd like to have. So it's kind of hard to have both of those. And I don't know why I got picked to ask about ocean energy. I don't know a whole lot about that one. You're the fluid person.
Yeah, I can comment on that. I'll maybe touch on the thermal, because it sparked one of the most exciting things that we're working on, I think, in our lab right now, is getting away from direct electricity generation for some of these decentralized projects. So, for example, right about now, a couple of our students are in this village in Alaska, and it's cold and it's dark, and they don't need electricity, they need heat. They don't need electricity, they need light. And now, of course, electricity can mediate heat and light, but there also are other opportunities to directly use the kinetic energy of the wind to generate heat, or to use the kinetic energy of the wind to generate light. And if you can do that for our wind turbine development, it simplifies a lot of things. We spend a lot of time and infrastructure costs on trying to take this variable generation and get it to a nice 60 hertz power that can be used. When it's a thermal energy source, the thermal actually serves as a buffer, but also a storage capacity for these villages. And so I think there's some interesting opportunities to hybridize the sort of thermal aspect with wind in a way that hasn't really been used in the large scale systems, because it doesn't make sense for the large megawatt scale turbines, but actually could work quite well for these smaller systems. To ocean, just briefly, I'll just note that the same physics that I talked about in terms of the interactions with these wind turbines, it occurs underwater, and so we're working with a couple of other research groups on underwater turbines that would generate energy in a tidal context in almost the exact same way. Wave energy it's a tough cookie. The ocean is a very difficult place to work, corrosion, and so on. And also, just from a practical standpoint, we found when I first started moving into energy, we were looking at doing something in the ocean, but it's hard to find a spot on the beach where people will let you install your newest device. It's much easier to find space to do wind, and so that's frankly how we ended up in wind.
So maybe I'll say a little bit more about that. So we've heard about waves, we've heard about tides. There's also ocean thermal energy gradients. It's warm at the top, cold at the bottom. There's also marine bioenergy that is harvesting things like algae and so forth. So in the Global Climate Energy Project, one of the first things we did is we did a systematic analysis of the size of all of the global energy resources relative to human energy demand. And it turns out that if you look at all of the marine or ocean energy sources, they're only from around 2 to say 5 times bigger than the total human energy consumption in a year, or the power is only. So basically there's not that much. So if we, for example, powered a significant fraction of our energy system with oceans, we would be extracting an important amount of energy that is probably playing some other important ecosystem function. So when you really look at renewable resources, that there are 2 that are very, very large compared to human energy use, and that's the sun and the wind. So at the end of the day, oceans might provide some local solutions for particular contexts, but I am doubtful that they're going to scale to the size of the global energy system and have large impact.
Thanks, Sally. Go ahead.
Hi, Mihaela Karste, Carbon 6, and I have more on the horizon or big picture question. Yesterday, the National Intelligence Council released their 2035 Global Trends Report. They still identify water and food insecurity as major threats. And I had a question about what do you see the role for clean energy R&D to address better integration with the energy, water, and ag sectors? And I'm thinking here things like maybe CO2 water recovery or CO2 use in agriculture and plenty of others. Those would be just 2 examples in light of Sally's comment on energy systems integration. How do we think at sort of systems integration at a larger scale? Thanks.
Great question.
Yeah, I mean, I think the context in which I've seen this has primarily been in the developing world, where you see the use of solar energy or wind energy for solar pumps, for example, irrigation in India. There are a couple of really exciting startups in that space who are trying to use renewable energy to improve the capability to farm year-round as opposed to just in the rainy season. Practically, I think one of the challenges is making a sustainable business out of those types of efforts. Right now, a lot of them are funded by nonprofits or other organizations, and so it's a net, sort of net negative in terms of the finances. How to make that a sustainable business, I think, is a good question.
Another issue is that we use a lot of energy for water, and we also use a lot of water for energy. I think the energy water nexus person. I mean, I love wind and solar because they're basically power supplies that don't require any water, and any time we can avoid use, that we provide water for other applications or protect ecosystem functions. So I think that's certainly important. I think that's the frontier, is this integration amongst energy, water, food, environment, and that kind of integration is the way, the systems thinking that we need leading into the future.
Yeah, so as Sally mentioned, we have the Department of Energy's Energy, Food, Water Nexus person, so you should ask her afterwards. Mike, did you want to say something?
Well, yeah, I think in that context, something we really haven't talked a whole lot about today is biofuels, having plants absorb sunlight and generate some fuel. And I mean, I think you have to be careful about not going too far with that, because we want to use our best food producing land for producing food. So, I don't completely oppose biofuels, but I don't support heavily using it. And maybe a number that not a lot of people know, plants harvest about 1% of the sunlight's energy, and solar cells that you can buy right now are at 16 to 20%, and I'm talking about raising that to 25 to 30. So solar cells, and solar cells don't need to be on flat, high quality land with local water supply. So of course I'm biased, but I think solar cells are the way to harvest sunlight and generate power, and we should be using our best land for food.
And I do think that there's a real risk if we create perverse incentives for producing biofuels or wood pellets or whatever for European or North American energy applications. We run the risk of really cutting into food supply and water and so forth. So I think we have to be very, very careful about thinking about setting up those kind of incentives.
Any more? Yes, let's take a last one here and then one from Chris.
Hi, I'm Karenza Gimri. I did my master's in atmosphere and energy at Stanford. I was interested in this trend of large companies shying away from investing in R&D and more of the onus falling on research universities or other smaller groups. There's an argument that increased regulation can incentivize companies to invest in R&D and spur innovation. But given that we probably won't see increased regulation, at least at the national level, over the next 4 years, do you see this trend of companies shying away from R&D continuing, or do you see some other factor coming into play that could encourage large companies to invest in R&D?
Who wants to kick it off?
I do see it continuing. I mean, if you just look at, a lot of investors are looking for short-term returns. I mean, most people probably don't even know where their money is invested because it's in a mutual fund and they probably don't follow it closely. And what that means is when you're investing, you're not really thinking about the long-term health of the company or whether what the company does is good or not. The people who are actually making the investments, their only responsibility is to get the maximum possible return for the people for whom they are investing. And if that's the drive, then you're not thinking about the long term. You're thinking about the next quarter. And I'm not aware of a whole lot. I think that's a very serious problem, although it's not the kind of problem I personally work on. And I'm not really aware of a whole lot that's being done to fix that problem. So I do see the trend continuing. And in academia, I'm encouraging more and more people to be applied. Another problem I see when I talk to people in industry a lot, and that's one of the things that makes Stanford special. We're in Silicon Valley, so we talk to companies all the time, and we get a lot of feedback. And they think a lot of university professors are very idealistic, very out of touch with what is really happening. But I think at Stanford, we're more in tune with that. And then by doing more applied research, we really understand, what the needs are. And I think academia does need to shift in that more applied direction. And because also really our job is to educate people. So we need to understand what the companies need, since they're going to be, only about 5% of our people are going to stay in academia. So if 95% of them are heading into industry, we need to be preparing them. And so there shouldn't be a huge disconnect between what companies are doing and what the universities are doing, in my opinion.
So I think that companies find it easiest to make long-term decisions in a world where there's certainty. And I think right before the election, I think there were many companies who were very certain that we were going to continue decarbonization, continue efficiency improvements. And my interactions with many of them indicated that they were taking a serious look at what they needed to do to be competitive, going forward, 10 years and so forth. I don't think decarbonization could be the only motivator for investment, but certainly certainty, I think, is key. I mean, if, for example, companies were challenged to bring manufacturing back to the United States, well, just copying what's done in China or someplace else is not going to be competitive. So if there were some real certainty of a driver like that, I could again see companies making the investment, but they have to have a good reason to do it. And I think the worst thing is when there's sort of flip-flopping back and forth, it makes it impossible to act.
And I'll finally say, David Hart and I have a report out explaining, how the Trump administration might encourage private sector investment in innovation. And you're right, we may not see new regulations that pull innovation into the market, but there are ways that we can push it in. For example, we have these great federal resources at national labs that we can make more available to private companies to leverage. And by bringing private companies together with diverse actors at hubs like national labs, for example, with academia and with federal researchers, we can encourage them to participate if they see somebody else also with skin in the game, namely the government. So I think there are ways to push for more private investment.
Chris, you've got the last word here.
Thanks. Actually, the question I want to ask is sort of where we go in the slightly longer-term future. It's probably a good way to close. There have been all kinds of amazingly interesting comments about next stages of integration of the clean energy resources, and it's relatively straightforward to inject additional renewables into a primarily fossil grid. And you've talked about 4 possibilities for large levels of renewable integration, and that's grid integration, demand side management, some kind of storage, and baseload generation. But not. I guess my question is how do we stimulate those things? Where are the next limiting factors, and what's a pathway by which we might elevate the capabilities of each of those technologies to be able to accommodate the large levels of renewables that we're talking about having on the grid within the next few decades?
Sally, do you want to kick it off?
Yeah. Well, that's a hard question. Again, I think the certainty is really a key factor. That, I mean, right now, some people feel like they're being pushed just to do what we're trying to do. The 10, 20, 30% renewable generation. But people faced with the idea that it's 50% or 60% or 70%, I think it stirs the creative juices and creates an environment. I think that, to a certain extent, places like California with its storage mandate, energy storage mandate, where it said, a couple of gigawatts of storage on the grid. I think that will be very helpful because we'll learn, it's not that much and so forth. So I do think that policies can be technology forcing. So I think that's useful. I mean, I don't think you want to push too far outside the headlights. But I think that really, another one is a carbon tax. I think that the idea of a carbon tax that starts at some level and progressively goes up with certainty, again, will stir the creative juices that get people really thinking about how we do this. If you think about the refrigerator example, back in the 70s, and, it was like, it was going to be impossible to make refrigerators more important. Well, what do we have? They're, like 3 or 4 times more efficient. They cost less and they're bigger. So innovation is possible if people set their mind to it.
So I think we may be close to calling an end to the panel. I'd like to ask if any of you have final remarks you'd like to give to sum up the discussion, any final lessons we should take.
Well, I wouldn't say it's necessarily a summary, but I would point out that the majority of people who are going to be consuming energy and emitting CO2 are not in the US. And so we have a very Western focus in a lot of our conversation, but rural India is probably not going to use advanced nuclear. China's not going to use rural China CCS. So I think we have to remember that the problem is much bigger than the United States of America, and think about technological solutions that are going to make sense for the broader world, the 1.5 billion people who have no access to electricity today, hundreds of millions more who are using biomass and kerosene and things of that sort. And hopefully in the process of solving that problem, we might find some solutions that are also applicable and helpful here in the West.
Thanks, John. Mike, any closing remarks?
Yeah, I think renewable energy is very exciting and has a great future, and I think it's not a question of if, it's just a question of when, and why not go ahead and do it and switch over to the clean way that goes on indefinitely, and I think the sooner the better.
Thanks, Mike.
Yeah, I'll just say, I think John is exactly right. We tend to be very myopic in this country about, the global energy system, and really the challenge is with the people who have no access to energy today, and perhaps even more urgently, the growing middle class around the world that, is starting to consume like we do. And so I think that's really important. And anyway, just one final thing, both John and Mike, you guys are so fabulous. These guys are literally on the cutting edge, not giving up when everyone says, oh, well, it's impossible, or, oh, it's already been done. And actually, both of them are doing that. So thank you guys for doing such a great job.
And I'll finally, I'll close by saying, I am very optimistic because I think now is really the time for universities to shine. Recently at Stanford, when I listened to one of Sally's presentations, I learned about the cool hidden surprises that universities can surface. For example, a battery researcher in Sally's institute discovering that his rolls of battery film, what he uses to make electrodes, could be repurposed to make clothes that cool you. Totally random connection. Here we have, a one-man random connection machine connecting fluid mechanics, biology, and energy and environment. In Michael's case, you have perovskites, which are, by the way, not just used for solar cells, but could also be used for LEDs and all kinds of other optoelectronic applications. And Sally's program, GCEP, and her ongoing efforts have been used to fund just a wide variety, a panoply of different energy technologies. I'm super excited that universities are going to be where we surface brand new connections, and I'm thrilled that the three of you are willing to share your expertise with us. So please join me in thanking all three of our speakers.
Let me close with my personal thanks to John and Mike and Sally and Varun. A wonderful series of insights. And let me just close with two thoughts. One thought is that we now know that for addressing the climate problem, whether we want to stabilize warming at 1.5 of a pre-industrial or 2 or 2.5 or even 4, eventually CO2 emissions need to go to 0. They don't need to be dramatically decreased. They don't need to be decreased by 80%. They need to go all the way to 0. So this is a problem that needs to be solved regardless of what our warming target is, regardless of whether we say we want to address climate change today or tomorrow. We need to solve the problem. But a second, and I think even more encouraging consequence of today's presentation is that I think we've really turned a corner from thinking about renewable energy as sort of a semi-acceptable alternative to the reliable fossil energy we have, to really understanding that it is, in a very deep sense, the good stuff. Renewables are what provide energy security, they're what address the climate challenge, they address a large number of acutely damaging pollutants, they can provide a wide range of jobs, and they can deliver energy potentially at lower costs than fossil alternatives. And I think that the recognition that we need to solve the climate challenge, and the recognition that increasingly renewables are the good stuff, really provide bookends to an amazing set of opportunities, and they're opportunities that are compelling whether you're in the business sector or the NGO sector or the government sector. Let me just close by thanking all of you for a wonderful set of questions and for helping us think hard about where the issues and the opportunities are. I want to thank the great Stanford staff that contributed to that. This includes Lee Rosenbaum, who leads our Washington office. Molly Field and Roberta Tugendreich came all the way from California to make today's event a success. Thank you. And thanks to all of you. I do hope that you will join us for the next of our sessions on addressing the environmental challenges of the 21st century on January 30th. We'll be back here looking at climate adaptation with a keynote from Marcia McNutt, the president of the National Academy of Sciences. Thanks again. Look forward to seeing you soon. Thanks so much.